Right, guys, check. We'll discuss about periodic properties, right? I'll share these notes after the end of class. So, long form periodic table, right? These are few important pointers which we need to know first. Okay, how does the things change from left to right and down the group? Atomic radius, left to right, it decreases. Down the group, it increases. Similarly, I would suggest all of you to go through them once thoroughly. What would happen in all the cases? Okay. Now, another important point which we need to keep in mind is the naming from 104 to 109. What is their common name? What is their IUPAC name? Sorry, sorry. Rather, I would say this is the IUPAC name. This is the IUPAC name. This is the number name. This is the number name. Okay. And I'm sure all of you do remember that what do we use the number naming as? Okay. When to use nil, right? Bi, tri, and ium, correct? Penta, hexa, septa, octa, and n. 9 is for n. Next. This is some important facts which you need to remember. One, starting with lowest electronegativity, highest electronegativity, smallest ion, largest ion. Okay. The other day there was a question about H minus and F minus like that. So you can check out what is the smallest and biggest ion. And other than that, in a group, what you need to know is what is amphoteric metals, what are metalloids, right? How many amphoteric oxides do we have? What are neutral oxides, right? And what is the isomorphism substances? Next, which has the density higher or lower, correct? So, which is the first man-made element, technetium. So these are few things I would suggest you to just go through it once. The periodic table goes back to the history of Lavoisier, where he categorized first elements in the form of metals and non-metals. That is how it started. And there was a brief understanding that if electrons are lost, it is metals. If electrons are gained, it is non-metals. So these were typical elements, and these were typical non-metal elements. Sorry. After that, Prout's theory emphasized on making every element which is made up of hydrogen atoms only. And if the atomic weight of H is 1, all others are integral value of hydrogen. Carbon, everything, nitrogen is made up of hydrogen. That was the hypothesis. Next is Daubigny's triads. So it is the set of three elements which give the same chemical properties. These are called triads. Okay. Central atom of the central atom of this group will have average of first and last element. Like chlorine, bromine, iodine. Bromine should be in the middle. It means the average molar mass of bromine is pretty much close to that of the average of these two. Okay. Similarly, average molar mass of strontium, which is pretty much close to barium and calcium. Sodium is average, having closer values to potassium and lithium. Other than that, they are able to recognize these triads as well. Okay. This is one standard example that will be coming in exam. So learn the pairs. Okay. This triads. So these three as one triad. This is as one triad. This is as one triad. Next, these are the other four examples. Okay. Next, Newland's octaves. Newland's octaves is about the property repeating after every eighth element. So lithium here. So 1, 2, 3, 4, 5, 6, 7. The eighth element is sodium. In that case, there were no description of noble gases. So elements was more or less without noble gases there. So lithium, sodium, potassium had a similar repetitive properties logic applies the same for beryllium, magnesium, and calcium. But unfortunately, after calcium, this kind of uh, mannerism or this kind of similar properties were not observed later on. So therefore, this one is pretty much valid only up to calcium. No inert gases included, no D block included. So it has its own drawbacks. Lothar-Meyer curve is about plotting atomic weights versus atomic volumes and concluding the graph. Atomic volume versus atomic mass, it gave us an idea that group 1 are always going to stay on the peaks. Just descending from there, you will get group 2. Ascending towards them, we will get group 17, which is halogens. So fluorine, chlorine, bromine are at the ascending levels, and group 2 are at the descending levels. Most electropositive elements are these, less electropositive elements are these, depending upon the peaks. Got it? This was the typical ratio that was identified. Okay. Based on this ratio, he was able to figure out what are the group elements: lithium, sodium, potassium, copper, rubidium, silver, cesium, gold. They all were identified at peaks. Beryllium, magnesium, calcium, zinc, strontium, cadmium, barium, mercury. They were all identified at the descending places. Like that, they were able to figure out boron, carbon, nitrogen. Okay, then we have oxygen, and we have group 17. Group 17 was also identified. Okay, hydrogen and helium were exceptional. Their masses, they were nowhere related to this table. Okay, neon, argon, krypton, xenon, and radon were also being part of table. I mean, they were pattern identified. Okay, so more or less, this give a lot of insight about how to view the atom and how to compare the atoms. Okay, and that's where you will see. Uh, correct? Sorry, the periodic functions of the elements and their periodic functions are basis of their atomic weights. This was what was originally proposed by Lothar-Meyer curve. And Mendeleev just took that and tried to expand it and made it into a little better fashion. So he said that the physical and chemical properties of periodic functions are based upon their atomic weights. He was able to identify 63 elements in which inert gases were unknown in state. He arranged in which vertical and horizontal columns were observed. Rows were 7, columns were 8. There were 7 rows and 8 columns. Just a minute. Hello. So we could see that in Mendeleev's periodic table, okay, each group will have A and B as the subgroups. A will have normal elements, B will have transition elements. The elements which were missing in periodic table were gallium, scandium, germanium, and technetium, which we call them as Eka, aluminum, boron, silica, and manganese. Okay, so this is again one area that would be asked during exams and mains. So please remember these words and what exactly it is replicating. Okay, next. He was able to identify atomic weights based on the equivalent weights and their reactivity. Okay, and the weights of the atomic weights were corrected to the nearest integers for these elements. Okay, uranium, beryllium, indium, gold, and platinum. Again, this is another thing which you will remember if by chance it is been asked. Which were the atomic weights which were corrected? Okay, next. Atomic weights which violate the Mendeleev's arrangement That includes potassium and argon. Okay, because as per increasing atomic mass we have to arrange, but argon and potassium is almost the same mass, close by mass. Technetium and indium, again this is violating. We are placing indium first and then technetium next. Next we have sorry, I mean technetium first and indium next. Yeah, I mean iodine next. Next cobalt and nickel, if you notice, same thing, their masses are extremely close by. And thorium and palladium is also very very close by. So if you notice this, not palladium, this is sorry, pm, promethium. So these are the values which you will notice. Okay. Hmm. Next comes modern periodic table, which is suggested by Moseley, where he incident light with high intensity, which was able to release electrons even from the inner shells. From the inner shells, if the electrons are ejected, they come always in the form of X-rays. Okay, so if the high intensity light falls on nickel, the rays which you are getting, this one, let's say, is gamma 1. This has a frequency gamma 1, gamma 2, gamma 3, like this, which means every metal is able to give different type of radiation, different type of X-ray radiation. All of them were giving X-ray only, but they have different frequency of X-rays. Okay. So as they move from lighter to heavier elements, the mathematical expression which he was able to identify, comparing all the frequencies, was under root of nu is equal to a into z minus b. A and b's are called the Moseley's constants. So under root of nu, which is frequency, is directly proportional to atomic number. So he was able to figure out some kind of a pattern is established here. Okay. From there, he said that all the elements arranged in an increasing order of their atomic numbers have a similar repetitive properties after regular intervals. So he was able to notice that 9 vertical columns and 1 to 8 and 0 group, these were the vertical columns, which are groups. Then inert gases were introduced by Ramsay later on, and 7 horizontal rows were there, which we call it as periods. Okay. This is the basic hypothesis of what do you say, Moseley's periodic table. Next, if you notice long form periodic table, this long form was completely proposed by, I mean, which was completely made by Bose, Bury, Rang, and Warner. Okay. And they finally suggested it as 7 periods, but with 18 groups. Okay, 18 groups include this 1A, 2A, 2B, 4B, 5B, 6B, 7B, and 8B. 8B has 3 columns in it, 8, 9, 10. Then 1B, 2B, 3B, 3A, then 4A, 5A, 6A, 7A, and 8A. So this was total 18 groups which we had. Okay, right. And you will notice that first period, which we call it as 1s shell, has 2 electrons, and these are those 2 elements, and that is the shortest of all. Okay. Second period has 8 elements, lithium to neon, that is also short. Third one, sodium to argon, short. Fourth one, potassium to krypton, long. Fifth one, rubidium to xenon, long. Sixth one, cesium to radon, that is longest. Okay. And francium to UNB, that is also a longest one. And this one is still going on. That means out of all, if you were asked longest means, sixth one is the longest, seventh one is still continuing. Okay. Some missing elements might be still there. Got it? So if you notice any periodic table, we will see that we should be able to categorize them into 4 blocks. One is S block, then we have D block here, this is P block here, and then we have F block here. These are the block elements. Okay. Now we must see what are the basic ideas behind those blocks. Okay. Let us understand that first. S block. The last electron is entering always in the s orbital. Then only we announce them as s block elements. The general configuration is ns1 to 2. There are two groups in it, alkali group and alkaline earth metals. And group 1 is having francium and group 2 has radium, and both of these are radioactive in nature. The last ones. Hydrogen to cesium, these are all metals except hydrogen. Beryllium to barium, these are all metals, except radium, which is radioactive, and francium in the first group. Okay. Clear, everybody? Just to add on to that, these are typically called as the soft metals, highly reactive metals, highly reactive metals, as well as okay, high electropositive, electropositive metals. Okay. When it comes to p block, this will be the last electron entering into p orbital. General configuration is ns2 np1 to 6. It starts from 3a to 8a. 8a is also known as the zero group. Then metals we will have, and non-metals we will see, metalloids we will see. Group 13, take boron always as non-metal, rest of the four as metals. That will include boron family, boron, aluminum, helium, indium, and thallium. Just a second. Sorry, guys. Check. Next one is group 14. This one is called boron. First one is called boron family. Second one is crystalloid family. So carbon is non-metal, silicon, germanium metalloids, and tin and lead being metals. Group 15, if you notice, first two are non-metals. Arsenic, antimony are metalloids. Bismuth is metal. We call them as nicogens. 16, first three are non-metals. Next two are metalloids. Tellurium and polonium. These are chalcogens. Group 17, all of these are non-metals. Astatine is metalloid, and these are halogens. And group 18, everything is non-metal, and these are noble gases. This is a briefing of P block, which we need to know. Next, D block. As the last electron enters into d orbital, we announce them as d orbital electrons or d block elements. General configuration is ns1 to 2, n minus 1 d 1 to 10, and np 0. That's it. Okay, so except palladium, which is supposed to be 5 is 0 and 4 is 10. D block, we have 10 groups here. All the elements present are transition elements except zinc, cadmium, and mercury. Transition elements means we should have a variable valency. Okay, that is, we should have a less, what do you say, we should have some variation in the number of electrons of d orbitals. Okay, if all the d orbital electrons are completely filled in any of their oxidation state, then those are called as non-transition metals. So zinc, cadmium, and mercury are those cases in which they have been non-transition in all the cases. Okay. Next, scandium to zinc. If you notice, scandium to zinc, that is 21 to 30. That will be 3D series. Yttrium to cadmium, that is 4D series. Lanthanum to mercury, that is 5D series. So all D block elements are categorized into series elements, 3D, 4D, and 5D. Next, F block elements here enter into F orbital. This is the general configuration. N minus 2, F1 to 14, 0 to 1, and NS2. All the elements are placed within the third group only, and they've been identified as two series. One is lanthanide series, actinide series. Lanthanide series starts from cerium to ruthenium. Okay, lanthanum is the only one which is like an, it belongs to D block, but also have some characteristic of F block. But if in the J, if the question is given, where does lanthanum belong? It belongs to D block, not F block. Keep that in mind. Same way, actinium belongs to D block element, not F block element, but that is like the starting element of it. So in the series, you will see that giving. Next, thorium to lawrencium. These are the actinides compounds. You see, both lanthanides and actinides are low abundance. We call them as rare earth metals. All actinides are radioactive elements. And elements after uranium, that is 92, these are called trans-uranium elements. All right. Next. Three important definitions which you need to know is one, what is a diagonal relationship? See, the second period element and the third period element, which are diagonally aligned in the periodic table, will have similar properties. Okay, it is to do with something called ionic potential, that is their charge by radius ratio. How much charge they hold, like lithium plus how much charge they hold divided by its radius. Similarly, magnesium 2 plus divided by its radius. That value, if it is same or very close by, that means they will have similar relationship. So lithium, magnesium will have similar relationship, beryllium, aluminum, boron, silicon, and by the time it comes to carbon, it diminishes. So diagonal relationship is, valid for the boron family only. Up to boron family, it is valid. After that, it is not identified or the property gets diminished. Okay, next. Typical elements. The third period elements, except the inert gases, right? These are called typical elements. That includes sodium, magnesium, aluminum, silicon, boron, sulfur, chlorine, all of them. Okay. These elements mainly represent the other groups. So that's why they are called typical elements. Got it? Represent as in their property is the first which will showcase in the compounds. Now, representative elements, sorry, these are not representative, I meant, sorry, typical elements. Representative means all S and P. Everything which is S and P are all representative elements. Here, the valence shell, right, should be incomplete. It should be less than 8. And S and P, except the inert gases, these are all representative elements. First, like I said, first man-made is technetium. First man-made lanthanide is promethium. Okay. Next. The difference between metal non-metal, just if you recall it once, I mean, it's just a basic thing. Most of the elements are metals, usually solid state. They exist in solid state at room temperature, except for mercury and gallium. They have high boiling point and melting point, except gallium, cerium, they will have very low melting point. Metals are, highly heat and electrical conductors. They are malleable and ductile as well. This is basic idea behind metals. Non-metals, they usually are solids or gases. Okay? Usually they have low melting point and boiling point except for carbon and boron. They are generally brittle, they are less malleable and ductile. Metalloids are somewhere in between both of them. These are the elements: silicon, germanium, arsenic, antimony, tellurium, and polonium. These are metalloids. Okay, just go through the IUPAC nomenclature once. Okay, all the elements and their official IUPAC name. What is their official IUPAC name? One question you will always get from here. Okay, in fact, this has become a norm in JEE mains also. One of the question always has been asked from 101 to 110. So learn starting with mendelevium, okay, nobelium, lawrencium, rutherfordium, dubnium, seborgium, borium, hafnium, mecnium, and dermostadium. Okay, mainly students make mistake in these two cases while writing 7 and 9. So just be careful with that. 7 means sept, 9 is n. Okay, not non or something, it is n. 4 is quad, rest all you know that. Just a second. Right. Let's see what are the parameters which have the trends over periodic table. First one is effective nuclear charge. Okay. Now, effective nuclear charge is how much a valence electron, I mean, whatever the electron your reference is, how much that electron is experiencing the attractive forces from the nucleus. So that electron experiences lesser attraction than the nucleus in case if there are any electrons intervening, if they are in between. So nucleus is getting completely shielded by inner electrons. Okay. The shielding of nucleus by inner electron is called as the shielding effect, and the net charge which this electron will possess, we call it as ENC, that is effective nuclear charge, or Z effective, which is equal to Z minus sigma. Z represents total nuclear charge, sigma represents shielding factor or a constant. See, this has been framed based on Slater's rules. Okay, according to Slater's rules, what you know? It is about how much screening factor every intervening electron is contributing. Okay, if you have the last electron for which you are identifying what is Z effective, imagine last electron is there. For that, you are identifying how much is Z effective. If there are any other electrons in the same shell, then they will contribute 0.35 units towards the screening factor. If they are in n minus 1 shell, the contributing factor is 0.85. Anything from n minus 2 on lower, they will always contribute 1. And if you are identifying screening factor only for the first orbit, in the first orbit, you'll maximum have 2 electrons. One of the electron will shield by zero point 0.3 units. That's it. This last statement is only valid when you are checking the Z effective on the 1s electron. Okay. Mainly remember the first three rules. Okay, first three rules, how it is Z effective. Now notice this. I'll give you an example here. Iron. The last electron is present in 4s. The last electron is present in 4s. In the valency, based on the valency. Karthik didn't understand, sir. Which part, beta? Karthik, please tell me which part. Can you explain this again? What is screening effect for that? See, if an electron is present on the outermost orbit here, let's say, okay, then every electron which is present in the inner shells, this one and this one, right, they will try to repel them, and thereby the nuclear charge on this one, that is the attractive forces on this electron, will decrease. So this decrease in the nature of the attraction is what we call it as screening effect. Alright, how much will it decrease? Depending upon two factors. One, how much is the actual number of protons present in it, which is what we call it as the nuclear charge. Second, how much is the decrease which is happening due to the electrons, due to the electrons in between those nucleus and the outermost electron, how much is the decrease in that charge? And that is what we call it as Z effective. For example, iron, it has 26 protons. So will the last electron receive the same 26 attraction, 26 protons attraction? No. That might be, that means there is something lost in between. How much is that attraction lost? That is called screening factor. Are they clear? Okay. Now, if you understand that, check out with an example. Example will help you understand more easier. Check out. Imagine the last electron is present in 4s. Okay. And in the same orbit, I have one more electron. So this one electron will give you a contribution of how much? 0.35 units. After that, I have n minus 1 electrons. These are all n minus 1 electrons. How many n minus 1 electrons we have? 14 electrons. And how much will they contribute? 0.85 into n minus 2. How many we have? 10 electrons and each contribute 1 unit. So how much is the screening factor? 22.25. That makes Z effective has 26 minus 22.25, 3.75. The last electron is only getting an attraction value of 3.75 protons. Everybody understood this logic? Now, for the same iron, imagine I'm trying to figure out how much is the Z effective on a 3D electron. Suppose if I want to find out how much is the Z effective on 3D electron. Now, 4s electron has no role in it because 4s is the next orbit, right? Outer orbit has no role. Now, the orbits and electrons between the electron, which is your reference, and the nucleus, between these two only you need to check. So you will see that. So between 3D and the nucleus here, these are the electrons present, and they will only give you screening factor. So for 3D electron, you will notice that first we will have 5 3D electrons here. 5 3D electrons we will notice. Got it? Now when it comes to D, there are total 6 electrons and 3D behaves slightly differently. 3D behaves slightly differently. So now you will have all 5 electrons from D that will have 0.35 contribution. Correct? Next, we will have 1s and 2s contributing to almost 1 unit. Okay, and we expect that 3s and 3p to contribute to around 0.85, right? We are expecting that to contribute around, sorry, we are expecting that to contribute around 0.35. One second. Okay, let's take here. Right. Okay. So if you are checking out for the 3D electrons here, for 3D electrons, the screening factor formula would always go like this. 0.35 into n. This is only for 3D, okay? Plus everything which is n minus 1 into 1. Okay? Everything which is n minus 1 and below. If it is n minus 1 and below, it will always have 1. So the same logic applied here also. So when it comes to screening factor, 3D has another 5 electrons plus everything which is n minus 1, n minus 2, everything which we have is total 18 electrons. That will give screening factor of 19.75. All right. And therefore, now the Z effective will be equal to 26 minus this amount, which will give us 6.25. Everyone understood this point? How? 3s2 and 3p6 is n minus 1. Second, let me check that. Once again, I'm mapping up with the electrons here. Is the calculation correct or not? I'm just checking once. Okay. The formula, just make a correction here. This is 3D, okay, 0 point and D only, ND. Okay. That is, these are the electrons of only D plus N into 1, where N is of S and P into 1 plus N minus 1 SP into 1 plus and so on. Okay. So please correct this formula. Okay. Now it is matching. See. So when it comes to the D block elements, okay, here is the simple correction here. Sigma should be 0.35 into ND plus N of S and P into 1 n minus 1 of S and P into 1 and so on. This is how it should be. So check it out.
So
That's
what about n minus 1d?
huh?
N minus 1d.
N minus 1 D also in this case. Okay, if it is D also, that is contributing 1. Okay, so all of that. Correct. So if you are taking it for 4D, you are asking, right? Okay. So if you are checking it for 4D also, then everything that is present in N minus 1 is supposed to give 1 only. Okay. Now notice for iron 3D1, if you remove, there are 5 more electrons which are present. So that 5 into 0.35 plus the rest all electrons which are present, they will always contribute to 1 unit. So that's how we'll get this as 19.75. And the Z effective on 3D electron is 6.25. On 4s electron, it is 3.75. While for Z effective, it is this much. Okay. We will once calculate one more example and see here just to ensure that what we are done is correct. We'll do it for zinc once, everybody. Why don't you guys try it with me? Zinc, we will have the configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2. Okay, this is the configuration, right? First, we'll calculate sigma with respect to 4s and sigma with respect to 3d. We'll see whether experimentally it is matching or not. Okay, so I'll put this as 4s1 and 4s1. Okay, so now how much we will have? There is one electron which is of a same unit, so 3.5, sorry, 3.0.35 into 1 plus n minus 1 we have 16, 18. So 18 into 0.85 plus 10 into 1. Okay, this is how much we have. Let me calculate that and see. 0.85 plus 10 plus 0.35. So that is coming out to be 25.65. That minus 30. So effective Z effective is equal to 30 minus 25.65, which is coming out to be 4.35 units. Now we'll do the same thing for D block now. If I put the same thing for D block, so in that case, now this will be 3D9 and 3D1 and 4s2. Okay, so this is my reference atom now. With respect to that, all the inner ones, how much it is contributing, we need to check. So 9 into 0.35 plus rest all will contribute same. So this one will be how much? So this is 12, 14, 16, 18. So 18 electrons into 1. So 9 cross 0.35 plus 18 electrons, so which is 21.15. So Z effective is equal to 30 minus 21.15. 30 coming out to be 8.85. You see the experimental value? Yes, it's matching. That is correct. Okay. I hope all of you understood how to calculate for D. For S and P, it is a regular case how we did that. Only D is this exception here. F you will not be asked. F has even more complexities. Anybody has a doubt on that? Okay. We'll do one for S and P also. Why don't you do it for potassium? Potassium 39. I have a right data in front of me here that you should get Z effective as 2.2. Check. This is wrong. Z effective. Check out. Right for Z effective of potassium, everybody. Ooh. Everybody quick. See 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. That's it. For this, we need to figure out so how much we are getting. Check these two, how much will they contribute for sigma? So we have 8 into 0.85 plus all of these three, 10 into 1. That is how much it is contributing. So we have 10 plus 0.85 into 8. So that makes it 16.8. So if this is the one, so Z effective will be equal to 19 minus, sorry, this is 19. 19 minus 16.8. So that makes it 2.2, which is correct. Everybody understood this logic? Right, let us go ahead now. So you will see that when it comes to iron here, so I just put some calculation there. So what is to be noted here is this one, beta. Lithium, potassium, sodium, rubidium, and cesium. Lithium, which will get Z effective as 1.3. Sodium, we will get it as 2.2. Potassium, you will get it as 2.2. Rubidium, you will get it as 2.2, which means except for group 2, except for second period, third period onwards, the Z effective remains constant. That is an important understanding. So you can see this is a general statement we can write. Down the group, Z effective remains almost same for all the elements. Again, assertion and reason question. These statements have been asked a lot of times. So learn. Down the group, Z effective remains same for all the elements, group elements. Since electron are added to the new shells, size will only increase because Z effective is not changing, but you are adding new shells. That's why the atomic size of these compounds will increase. Next, from left to right. Left to right, beryllium was found to be 1.95. Boron is found to be 2.6. So from here, you are noticing that left to right, the Z effective is actually increasing. So you can see the size will start decreasing. So that's why size is diminishing here. Correct? While towards the group, down the group, it is increasing, and left to right, it is decreasing. Whenever we calculate, we identify the size, there are four radiuses we can compare. First one is covalent radius. Covalent radius is half the distance between two nucleus where atoms are covalently bonded. The covalently bond must be a single bond here almost. So you can see this point to this point, this is a covalent bond formed. And covalent bond will be half of the internuclear distance. Like chlorine has an internuclear distance of 198. So therefore, covalent radius will be equal to 99 picometers. Heteroatomic. If you have heterodiatomic, then we will have to take total distance as Ra plus Rb. But it is only possible if both of them are same electronegative. But if there are electronegative differences observed, okay, if there are electronegative differences observed here, so between these 2 points here, correct. So then check it out. D of AB will be equal to Ra plus Rb minus 0.09 into delta of lambda. Okay. And here Ra plus Rb, this radius should be expressed in Armstrong units. This should be expressed in Armstrong units. And then only this formula is valid. So 0.09 into delta x. Delta x is nothing but electronegative difference. This is called Stevenson and Shoemaker formula. Again, direct questions will come, guys. Learn the formula clearly. Okay. Sorry, not Armstrong's. I mean picometers. Next, metallic radius. Metallic radius is the one which will have half of the distance between two metal atoms. Van der Waals radius, half of the distance between the two molecules. Between two molecules, if you have closest distance, that closest distance is intermolecular distance, that divided by 2. Okay. So covalent radius is 180. In non-metals, when atoms or molecules come close to each other, then they have certain defined intermolecular distance. Now, based on this observation, we find that the van der Waal radius is greater than metallic radius greater than covalent radius. In fact, covalent radius is almost 40% larger than, sorry, van der Waal radius is almost 40% larger than radius of the covalent radius of the element. You can notice that here, hydrogen has a covalent radius of 0.37, van der Waal radius of 1. Oxygen is 0.66 and the van der Waal radius is 1.4. Fluorine is 0.99 and 1.8 is the van der Waal radius. While comparing left to right, okay, the type of radius which defines the property of the element, if you notice, you can see that lithium, which has atomic radius 1.152, but that is metallic radius. These are all in ppm. Okay, in ppm. In picometer, not ppm, in ppm. Rm, this is the metallic radius. Beryllium also is a metallic radius. Boron, carbon, nitrogen, oxygen, fluorine, and neon. They do not showcase anything like a metal. Okay. Sir, in heterodiatomic in covalent radius, half of internuclear distance. One second. Sorry. Sir, in heterodiatomic is the covalent radius half of IND calculated also. No, beta. In hetero, if the electronegative difference are there, then you have to use Shoemaker formula. Okay. Next. Shielding effect by subshells, you will notice that generally NS will have greater than NP, ND, and NF. Acha, I forgot to explain this one, that how the atomic radius changes. You see, the atomic radius is actually decreasing, but it will decrease up to fluorine. After fluorine, again it will start increasing. Got it? So while comparing the inert gas versus the group 17 one, you will notice that inert gas will always have larger atomic size. Next. Ns is greater than Np, Nd, Nf. This is due to the penetrating power. Okay. Next, ability to be closer to the nucleus, that is called as penetrating power, Ns, Np, Nd, and Nf. Now, if Z effective increases, right? I mean, Z effective increases in case if it is cations, Z effective decreases in case if it is anions. So Z effective usually varies this way. Negative charges will have less Z effective than neutral, then positive charge. So for isoelectronic species, Z effective will be highest in the case of boron, then beryllium, lithium, and hydrogen. Hydrogen plus here. Okay. Sorry. H. H minus only here. We need to have Z effective, right? Similarly, if you notice the Z effective in this case here, you'll see Z effective is highest for magnesium, sodium, F minus, O2 minus, and N3 minus. Next, group 13, if you notice, expected radius is this one, but the actual radius is this one. This is to do with multiple factors here, as in when we go towards the groups, we'll study that. But you will notice that the trend is not exactly the same as, simple increasing. It is not linearly increasing anything. So you can see boron, Z effective is 2.6, then 3.5, 5, 5, and 5.6. Okay. This is the Z effective value. Based on that, if you notice the size, atomic size of these elements here, correct? So you notice that when it comes to boron, then aluminum, then gallium, it decreases, in fact, okay? Towards indium, it increases, and towards thallium, it almost remains same or slight increases observed. That's it. So this is boron, aluminum, gallium, indium, and thallium. So this is how the radius versus elements will vary. When it comes to D and F block elements, usually for scandium to chromium it decreases, where Z effective is dominant. From chromium towards, chromium towards copper, it decreases again. It almost remain constant. Slightly on, sorry, this manganese is not exactly up. It is slightly down, very close towards this, and then it will decrease a bit here. Okay. So then you will notice that Z effective and sigma are almost equally dominant. So you will hardly see much difference in the size. And from copper to zinc, it will increase again. Copper to zinc, it will always increase. So similar trend is followed for 4D and 5D series also. Now this is important that when it comes to going down the group, scandium is less than yttrium, less than lanthanum. Correct. But that is not the case when you go for titanium, vanadium, chromium, and so on. Because when it comes to zirconium and hafnium, the size will almost be same. Niobium and tantalum, molybdenum and tungsten, in all these cases, the size would be same. This is to do with the fact that when it comes to 4f electrons, because in hafnium, tantalum, and tungsten, 4f electrons have been already filled, and that is going to give you a very poor screening effect. And due to which poor screening, Z effective increases drastically. And hence 4D and 5D elements of the same group show similar sizes. And this is what we call it as lanthanoid contraction. This is what we call it as lanthanoid contraction. And you see in lanthanides and actinides, there is a typical decrease in the size due to lanthanoid and actinoid contraction. Okay. So general ionic trend is always linear, guys. Ionic trend is always linear. That means from scandium towards zinc, it is linearly decreasing. And group also, it is linearly increasing. So chromium, molybdenum, and tungsten. Manganese, based upon the oxidation state, +2 towards +7, size will decrease. Okay. So I guess all of you understood, got an idea about how the ionic radii is. Yeah. Mainly today focus on reading out NCERT everybody.